Okay, so today's lesson is on angles of elevation and depression. So we're talking about looking up at things or looking down at things. Now, the angle of elevation and the angle of depression are always taken from the horizontal. So what does that mean? It means that in this particular case, the angle of depression is this guy in here, and the angle of elevation is that guy in there. Okay, so we just got to make sure we're aware of whether or not that angle falls within the triangle we're creating to solve the problem that we've got to solve. So in this case, actually what I just want to mention too as well is obviously the horizontal is always parallel to the horizontal. So the angle of elevation and the angle of depression will always be the same. They're just because they are alternate angles on parallel lines. You might remember from back when we were doing parallel lines a long time ago that when we're looking at alternate angles, we're looking at angles like this that are on the other side. And I think you probably would remember that we call them Z angles because they sort of go along here and along there and along there like that. So if you remember them as Z angles, but every angle of elevation has a alternate angle of depression that's the same size, and you can use that identity sometimes to solve some problems. So just having a look now at where we're at, the angle of elevation. So what is the angle of elevation of the helicopter from the car? So really important, where are we looking from? We're looking from the car. So the angle of elevation from the car up to the helicopter is beta. Okay. And what is the angle of depression of the car from the helicopter? Remember, look for that word from. Where are we looking from? We're looking from the helicopter, so we're looking down, and that means we're using alpha. And explain why alpha equals beta. Something like because they are alternate. Can't spell. Because they're alternate angles on parallel lines would be a suitably good answer. Now, what this usually creates, obviously when we're talking about angles of elevation and depression, most of the time we're talking about height. Heights are usually measured 90 degrees from the ground. And if the question's about a tower or a cliff or any kind of structure that you expect to be upright, you can assume that that structure is in fact upright and is at 90 degrees to the ground. Okay, so we've got a situation here where Joe's standing 40 metres away from the base of a 25 metre tall tower. And what is the angle of elevation from Joe to the top of the tower? So we're trying to find this angle in here. So we've got a situation where relative to this angle, we've got an adjacent side and we've got an opposite side. And we're trying to find the angle just like we did in the last lesson. So if we're dealing with the opposite and adjacent, we use SOCAR TOA. Tan involves the opposite and the adjacent. Please get in the habit of just writing down the formula in this form. So just before you start substituting numbers, just write it down so you know you're going to get it right. So in this particular case, I don't actually know what theta is. That's what we're trying to find out. But I know that the opposite is 25 and the adjacent is 40. And so I'm going to end up with theta equals 10 to the minus 1 of 25 over 40, and at this point I can pick up my calculator and plug that in. So remember, shift tan to get an angle, 25 over 40, close my brackets, and my answer is 32 degrees. Now importantly, does it ask for? It just says what's the angle of elevation. Given it's so low, so close to 32 degrees exactly, we'll probably just round it to 32 degrees. So 32 degrees, and we'll just write that's to the nearest degree. Okay. Now in our next example, the angle of depression of a ship from the top of a 220 metre vertical cliff is 32 degrees. Find the distance of the ship from the base of the cliff correct to 1 decimal place. So we're looking for this distance down the bottom here, D. Now the first thing we're going to realise, of course, is if it's at 90 degrees, there's a 90 degree line there. Every horizontal is 90 degrees to every other horizontal. So that means the angle in triangle equals 90 degrees minus 32 degrees, because that angle of depression is not actually in the triangle that we're trying to find the distance for. So that's going to be 90 minus 32, that's going to be 58 degrees. Okay, so now that we know that we know this angle here, we know that's 58 degrees. Then relative to that angle, we've got an opposite side and we've got an adjacent side. So once again, this is an area where tan comes in. So tan theta equals the opposite over the adjacent, but in this particular case, we know the angle, so it's going to be tan of 58 degrees equals the opposite, which we don't know, that's just D, over the adjacent, which is 220. So in other words, I'm just going to change sides here. D equals 220 tan 58 degrees. And once again, we plug that into our calculator. And we get 352.07. The question, does it ask us for an answer correct to 1 decimal place? So 352.07, the 7 is going to round that 0 up, so it's going to be 352.1. The units were metres, and obviously to 1 decimal place. Okay, and example 4, which is a little bit more involved, involves a person looking. So Alex is over here. I'm just going to put a big A there to show that that's Alex. Is standing on the roof of his apartment block and sees a bird on the roof of a neighbouring office building at an angle of 14 degrees. At the same time, he sees a dog at the bottom of the office building at an angle of depression of 33 degrees. So obviously the distance between the two buildings is going to be the same up here, up the top, as it is down the bottom. So either way, the distance between the two buildings is going to be 280. So how far it is the bird from Alex? Well, essentially, I'm going to say let distance from Alex to the bird be x. So I'm going to say that's our x along there. All right, that's the bit we want to know. That's the straight line distance between Alex and the bird. Now, I know that the distance at the bottom of that triangle, if I think about that triangle just as a triangle on its own now, I know that that's x. I know that this is 14 degrees. And this distance here is 280, because the distance between the two buildings down at the street level will be the same, given the type of buildings they are, they'll be the same up at Alex's level from the roof of the building. So given that's the case, I've got an angle, I've got an adjacent side, and I've got the angle opposite the right angle. There's the side right opposite the right angle, which is the hypotenuse. So I've got an adjacent and a hypotenuse. So in that circumstance, I'm going to be using cosine. So CAH, C-A-H. So cos theta equals the adjacent over the hypotenuse. And in this particular case, that's cos of 14 degrees equals the adjacent side, which is 280, over the hypotenuse, which is x. Now, once again, this is that situation where if the unknown's in the bottom, you can just do a swapsy, or you can do your algebra to work it out correctly. But if you remember that, then you can just jump straight to x equals 280 over cos 14 degrees. And we plug that into our calculator. So 280 over cos 14 degrees. And we end up with 288 now to say what the accuracy was, no, we can choose ourselves. I'm going to go to 1 decimal place, so 288.6 metres. Okay, so that's relatively simple, but now how far is the bird from the dog? So the bird to the dog is going to be this distance all the way down here. Now, it's probably going to be easy to break that up and say, well, let's find this distance here, and then let's find this distance here, and add them together. All right. Now, in both cases, I've got triangles with angles, and in both cases, this distance here is 280 meters. So what I've actually got is a strange situation. In both of these, if we think about it, so for the top triangle, so if we call this distance here, I'm going to call this distance here y. Oh, I'm going to do it in the same colour as what I did it before. I'll call this distance here y, sorry, and I'll call the distance up the top z. Okay, so if that's the case, if I go with the purple first, so in the top triangle, I've got, what have I got there? I've got relative to that angle, I've got an opposite and an adjacent side, so tan theta equals opposite over adjacent, and in this case I'm going to have tan 14 degrees, I think it was. Yep, equals opposite over adjacent. The opposite side I don't know, I called that z, and that's over 280. Yep. So I'm going to end up with z equals 280 tan 14 degrees. And then in the bottom triangle, I also will use tan, so I've got an opposite side and an adjacent side. So in bottom triangle I have tan theta equals the opposite over the adjacent, and in this case it's going to be tan of, I think that was 33 degrees. Yep, equals the opposite side, which is y, over the adjacent side, which is 280. So we end up with y equals 280 tan 33 degrees. Now in this particular case, I'm going to bring those two together. So I'm going to, rather than work those out, I'm going to say therefore x plus y equals distance from dog to bird okay, which in this case is going to be equal to it's not x plus y, z plus y, my apologies. I'll do a bit of z too. So in that case, it's going to be 280 tan 14 degrees plus 280 tan 33 degrees. And I can just plug those into my calculator. But rather than doing all those calculations and keeping those weird numbers in my calculator, by waiting till the end here, I do the calculation just once. So 280 times by tan 14 degrees plus 280 times by tan 33 degrees. And we press equals, and then it'll give us a nice easy number to work out. So we'll go to one decimal place again, so 251.6, and that's to one decimal place. So we've got a nice little answer there. So yeah, a little bit involved in that one, but don't be afraid to draw over the drawings that are there, or create your own drawings for a problem. Try and make it as clear as possible for yourself to follow. That'll be the end of this lesson.